Hi everyone, I welcome you to this presentation on capacity of a cell. Okay, so capacity of a cell, the capacity of a cell, which is given in ampere hours, which is the rating of a cell, it will give you how much current can be delivered in a period of time. So it's just a product of current and time consumed. Okay, so you're supposed to measure the current used under a period of time. So the current is in amps and time is actually measured in hours. Okay, so it's just a representation of a battery. Okay, so in knowing the capacity of a cell, you're supposed to know its efficiency. So the efficiency by definition of any system is simply the ratio of the output to the input. So the efficiency of a cell has two forms. There is one which we are calling ampere hour efficiency or quantity efficiency, and the other one is what we are calling watt hour efficiency or energy efficiency. The difference between the two, given these, the difference would be, in the first one you have a cell or a battery, you are calculating the consumption in terms of power, which is in kilowatts. So you are supposed to measure the wattage during charge times the time. It will give you the kilowatt hour during charging. And then when you are using it or when it's discharging again, you take note of the kilowatts you are using times the period of time you are discharging your battery. Then for you to calculate the efficiency, it would be the kilowatts during discharge divided by the kilowatt hours during charge. So kilowatt hours during discharge divided by kilowatt hours during charge times 100, it will give you the efficiency. In this case, you will have 60% as your efficiency. Then the other type of efficiency is the ampere hour efficiency. With it, you calculate the time during charge and the current you are using. And then even on discharge, you calculate the time taken during discharge and the current you discharged there. So during charge, the current times time, it will give you a value which is in ampere hours, and during discharge you get a value which is in ampere hours. So for you to find the efficiency, you divide ampere hours during discharge divided by the ampere hours during charge. So for this scenario, we're having 98% as our efficiency. Okay, so the ampere hour efficiency, as explained in the previous slide, is simply the ratio of the ampere hours on discharge to the ampere hours on charge expressed as a percentage, and they are given by this formula. So the symbol for efficiency in ampere hours, you have that Greek letter and you put ampere hours to show that you are finding the efficiency in ampere hours. So you find the discharge amperes, the current during discharge, times the time during discharge, but the time should be in hours, current in amperes. Then during charging, again you take note of the current during charging and the time, which should be in hours as well during charging. Then these, in terms of symbols, they are represented by this. So the discharge current is represented by ID times the discharge time, it's ID. Charging current is IC, charging time is IT or TC. Then you have that. Upon having that, I would conclude the formula for the ampere hour efficiency. And then for the watt hour efficiency, it's the ratio of the watt hours on discharge to the watt hours on charge expressed as a percentage. So you take note of the watt hours, which is the discharge. So this VA means a product of voltage times current during discharge, and then during the charge again you multiply the voltage times current and then you multiply by time. You divide, that will give you the efficiency. So these are represented by that formula, VD, which is the voltage during discharge, times ID, current during discharge, times the time. Even during the charge you do the same. Then you find the quotient, multiply by 100, it will give you the percentage. Okay, then we come to the examples. So for example, a battery has a charging current of 5.2 for 24 hours at a voltage of 2.2 4.25 volts. While discharging, it gave a current of 4.5 amps for 24 hours at an average voltage of 1.85 volts. Calculate the quantity efficiency and the energy efficiency. So before we start calculating, we start analyzing the data. So this is what we've been given. We have the charging current, which is 5.2, and we've been given the period of time during charging. It was the whole day, like 24 hours. And then the charging voltage was 2.25. Discharge current, discharge time, and the discharge voltage, they've been given as well. So we've got two efficiencies there. We've got what we are calling the quantity efficiency, or the ampere hour efficiency, and the other one, which is the energy efficiency. So let's start with the quantity efficiency. So quantity efficiency is simply the ratio of discharge amperes times time divided by charging amperes times time. So from here, discharge amperes times time, it's found by the discharge amperage, which is the discharge current. It's 4.5. You substitute there. Discharge time is 24 hours. Charging current is 5.2. Charging time is 24. When you compute that in your calculator, it's going to give you 86.54 as your quantity efficiency, or ampere hour efficiency. And then we go to the second type of efficiency, which is the watt hour efficiency, or the energy efficiency. So for the energy efficiency, the formula is discharge voltage times current times time divided by charging voltage times current by time, which is presented by that formula. And then these were given in our data. When you substitute, you are going to have that. Okay, so what you can note is this equation, actually, when you don't put the voltages, it's simply the ampere hour, because this is the charging current and the charging time, charging current and charging time. Then we're just putting 4 voltages like that. So if you want, you can find the ampere hour efficiency, and then you multiply it by this ratio, discharge voltage over charging voltage. It will give you the watt hour, or basically just this. Then it's going to give you 71.15%. We go to example number 2. So 35 lead acid cells, each of discharge capacity 120 ampere hours at the rate of 24 hours, are to be fully charged at a constant current for 10 hours. So the DC supply is that, then the ampere hour efficiency is 80%, and the EMF of each cell at start and at the end. So you've got two EMFs here. You've got 1.9 volts and 2.6 volts. Calculate the maximum and the minimum values of the external resistance necessary, but you need to neglect the resistance of the cell. So in our solution, you come up with the data first. What have we been given? So we've been given the discharge capacity, which is 120 ampere hours. So in short, this is the current times time during discharge. So during discharge, current times time has been given to be 120. The time during discharge is 12 hours. The time during charge is 10 hours. The charging voltage is 125 volts. Okay, the efficiency is 80%. So ampere hour input, it comes from the efficiency. We know that efficiency in ampere hours is simply the product of current during discharge times time during discharge divided by current during charge times time during charge. So here we have the discharge capacity of a cell. When they were discharging, the product of the current and the time has been given to be 120. So when you divide that by the efficiency, it will give you the product during charge, which is the ampere hour input per cell. So the discharge is simply 120 divided by the efficiency, which is that. So this will produce 150 ampere hours. So this will be the input. And then we come to the charging current. So the charging current, we know that during charge, which is the input, we had a product which is 150 ampere hours. So they multiplied current times time during charge, it gave them 150 ampere hours. So when you divide this, the product of current times time, you divide it by time, you remain with the current. So this 150, we are dividing the charging time, which is 10 hours, it will produce 15 amps as the charging current. Okay, so the combined EMF of 35 cells, just as the question states, which are connected in series at the end of the charge, will just be given by, because we have these two, because they're saying EMF of each cell at start and at the end. You have this 1.9 volts, which is for the start, and 2.6 volts, which is for the end. Therefore, the combined EMF of 35 cells connected in series at the end of charge, it would be the number of cells times its EMF. So you're going to have that as the combined EMF, which is 66.5 volts. Okay, and then the combined EMF of 35 cells connected in series at the end now. So in your ending, the combined EMF would be the number of cells times the EMF at the end, which is the 2.6. When you multiply these, it's going to give us 91 volts. Okay, now the resistance which is necessary to be added in the circuit to maintain the charging current at a constant of 15 amps will be maximum at the start of the charge, when the back EMF will be minimum, and it will be given by that expression. So we know that resistance is simply voltage over current, but the voltage, we've got two voltages there. We've got the voltage which was given in the data there, which is 125, and the voltage which we had got at the start of the time, which was 66 on our previous slide. So you do the difference between those two voltages. While we're doing that, we want to find the resultant voltage, and then you divide by the charging current. So you're going to have 3.9 ohms as the maximum resistance, and then for the minimum resistance, it will be the same voltage which was given in the data minus this voltage, combined EMF of cells connected in series. Find the difference, it will give you a resultant voltage, and then you divide by the charging current, which is 15, and then that will produce 2.2 ohms. Thank you for watching.